Okay, let's talk about the applications of derivatives and related rates of change. So if you're watching this video, assume that you are looking to learn calculus. You're probably a calculus student in maybe some college, so that's excellent. Now, the purpose of this particular video is just to help you out and understand, obviously derivatives and related rates of change. We're going to be taking a look at a classic calculus problem that has to do with these topics. So something that if you are taking calculus, you want to learn it, you want to stick around and make sure you can solve this type of problem because it's, again, very fundamental and classic type of calculus problem when it comes to derivatives and rates of change. But before we get going on the problem, let me tell you a little bit about myself. My name is John. I'm the founder of Tablet Class Math. And basically my background is I'm a middle and high school math teacher, taught beyond that as well, and offer various math courses. I don't offer a calculus course, although I do calculus videos on my YouTube channel. So I have you may have come to this particular video from one of my other videos that I've done a while back. It was called Understand Calculus in 10 Minutes. It actually turned out to be like a 20-minute long video, but apparently a lot of people have liked it because I've had like over 3 million views on it. So that just kind of motivates me to continue to teach more on calculus. So I'll be doing that. Obviously, this is what will be one of my videos, but I want to recommend a great book to you that I own and have had for several years. And if you're taking calculus, you really want to get this book to assist you. It's called the Humongous Book of Calculus Problems. And it's basically, I think I got the title pretty much right. But anyways, I'm going to leave a link to that book in the description of this video. But that particular book, and there's others like that, this kind of book, but this particular book is really well done, and it goes over like 1,000 plus calculus problems, very like calculus 1 level type of problems, and it shows you step by step how to solve a lot of problems in easy to understand language. So if you're taking calculus, I would highly recommend that you pick that book. It's not too expensive at all, but it's an excellent reference. So again, I'm going to leave the link to that book in the description of this video. But with that being said, let's get into this problem here. So application of derivatives and related rates of change. So here is a very classic type of problem. Now, this isn't the problem in itself. I'm going to show you that here in a second, but it's going to be related to this scenario. So here we have a cylinder and we have fluid in it. Maybe it's water or whatever, right? So we have fluid in a particular cylinder, and this fluid, or the volume of this fluid, is going to be kind of removed, right? It's either going to be pumped out or we're going to just kind of leak it out. So it's going to come out the bottom, okay? And so you have volume being removed at some particular rate from a cylinder of fluid. And the question would be, well, how fast does the fluid level drop? So here we have the height, right? So here's the height or the level of the fluid. And as we start pumping this fluid out, how quickly does the height of the fluid or the fluid level drop respective or related to the volume being pumped out? Now you're saying, well, okay, well, we're moving volume. This is definitely going to be coming down. A lot of this would depend, obviously, on what type of cylinder, right? Or is the cylinder like, really skinny like this, all right? So if you had volume pumped out at a particular rate, maybe you would see the volume or the height, the fluid level drop faster versus like a big wide cylinder, right? Let's say you had a big wide cylinder like this and we're pumping out at that same rate. It might be like a slower to see the height or the water level or the fluid level go down, right? Kind of think of maybe some of you out there have swimming pools. You could see, and you have to fill up your swimming pool. It takes a long time for that fluid level to go up because it's a wide, it's longer. Swimming pools aren't built like this. If you're filling something up like this, it would go up quicker. We would see the height go up faster, right? So this is kind of an interesting type of problem, and it has to do with related rates of change because we have the change of volume being removed. Okay, so we have volume being removed, but at the same time we have height or the fluid level going down. Okay, so these are two changes that are concurrently going on, and this is a very classic type of calculus problem and a great application of the first derivative. So with that being said, let's get into an actual specific problem that's related to this scenario. So here we go. All right. Now, I'm going to assume that you already have some basic calculus knowledge. And if you don't, no problem. Again, all this stuff you can kind of learn. And then if you want to do more of these type of problems that I'm going to cover here, that book that I recommended would be an excellent start. All right, so here's our cylinder. And we want to know how fast does this fluid level drop, and then of course we have the fluid or the volume being removed. And let's say for this particular problem, it's being removed at 3,000 liters per minute. Okay, so it's being pumped out, removed in some manner, but the rate at which the volume is being pumped out is 3,000 liters per minute. And what we want to find out in this particular problem is, well, how fast does the fluid level drop when the volume of the cylinder is being pumped out at 3,000 liters per minute? So what that means in calculus talk, if you want to call it that, is we want to find what dH dt is. Okay, now let me get back. I'm going to hold that thought for a second because I want to come back over here. Okay, so we have this dV dt is equal to negative 3,000. All right, so obviously I kind of pre-wrote the solution here, but what does this dV dt means? Well, if you this is the rate of change, okay, in calculus. This is the first derivative. Okay, this is the change in volume with the respect of time. So as the volume is changing as time goes on. So the way we write this, and this is another way you can write this in calculus, is delta V over delta T, and this is the little d, but this is probably the most common notation to write that. So this is the change in volume with respect to time. But as time goes on, as we're pumping things out, the volume is changing, right? So we would write it this way: dV dt is equal to negative 3,000. Now, why the negative? Well, because we're removing the fluid, we're going to use a negative sign here. Okay, if we were adding fluid, it would be positive. Okay, so for this particular problem, the change in volume with respect to time as time goes on is negative 3,000 or 3,000 liters per minute. And what we want to know is, what is the change? We want to know dH dt. What's the change of the height? How is the height changing with respect to time? Okay, what's the difference of the height, or the change of height with as time changes? Okay, and now you have two rates of change, right? This is what we call related rates of change. You have something changing here, and you have something changing here over time. Okay, so this is again the perfect type of problem for calculus to solve. You need calculus to solve this type of related rates of change, and that is again a major, foundational concept of what calculus is all about. Again, if you haven't seen my other video, Understand Calculus 10 Minutes, I kind of talk about what calculus is in a much more fundamental, real basic type of way. So I want to check that out if you're a little bit kind of lost on, some of these more fundamental concepts. But anyways, let's get back to this problem here. So let's use this color here. So we have this, right? So this particular problem, we know that the volume is decreasing over at 3,000 liters per minute. So that would be our dV dt. And we want to know dH dt. Okay, this is what we need, right? Because this is the change of height with respect to time. So this is going to answer this question: how fast does the fluid level drop when you're taking out 3,000 liters per minute? Okay. All right, now let's move into the actual mechanics of the problem. All right, so here again, so we have dV dt, okay, this rate of change here, which is this, and we're looking for dH dt. So in calculus, what we need to do is we need an equation that relates both V and H. Okay, so here we have volume and we have the height. okay, of this particular cylinder. So we're going to need some sort of way to relate these two variables, V and H. And probably most of you were like thinking, oh, okay, yeah, the volume of the cylinder is equal to pi r squared times H, right? So here's the volume, and then here's the radius, and this is the height of the cylinder. So if you were thinking that, that's excellent. Okay, so this equation relates the V and the H. So we need some way to relate these two rates of change. So we're going to use this equation, but we're going to have to make a few adjustments here. And this is not trivial. This is really important for this particular problem. But let me get into what I'm talking about here. So again, we have an equation that relates the V and the H, okay? But the problem, and this could be, for some students, a little bit confusing, so I'm going to try to make it as easy to understand. So we know that the fluid or volume being removed is 3,000 liters per minute. So we know our dV dt is negative 3,000, okay? But we're dealing with a rate of change that has a specific unit of measure, and that's liters per minute, okay? So because we're using liters, then we need to, let's go back over here, because we're using liters, well, then we have to consider what unit of measure. Remember, this is a unit of measure here, okay? Liters, okay? Volumes being measured in liters, not gallons, right? If it was gallons or something else, it would be something different. So now we have to consider what unit of measure our radius and height are going to be. Well, we want to use meters because meters is connected to the unit of measure with liters, and specifically 1 cubic meter is 1,000 liters. So now we have to start kind of thinking about setting this up in terms of modifying this equation so we have the right units of measure going on here. So remember, the problem gave us 3,000 liters per minute. So we have to, that's a really, really important part of this problem. The units of measure is really important because we just can't use this equation as it is. We're going to have to account for the units of measure. So here we have 1 cubic meter is 1,000 liters. So we'll on our answer, we want our volume to be in liters, but here, I wrote this out here, just focus in if you will. I'm going to get back to this in a second. But here we have radius squared, okay, so that let's say this is in meters, right? So that's going to be meters squared times the height, which would be in meters. So here we would have meters cubed. Well, we want our volume. Our volume isn't going to be in meters cubed. It's going to be in liters. So we need to do some conversion here. So 1 meter cubed, okay, or 1 meter cubed here is equivalent to 1,000 liters. So hopefully you have some kind of experience with conversion factors. So we have 1,000 liters is equivalent to 1 meters cubed. So when we calculate this part out here, we get meters cubed, but we need to get rid of the meters cubed because our given information is in liters. So the way we do that is we multiply by this conversion factor right here. 1,000 liters is equivalent to 1 meters cubed. It gets rid of the meters cubed, and we're left with the unit of measure of liters. So you can kind of see that setup right here, because volume for this particular problem is given in liters. Remember, 3,000 liters per minute. So if we're using 3,000 liters per minute and we're using this as meters, well, we have to multiply by 1,000. Okay, so you can see here how this math works out. So really, the formula we're going to be using is this formula right here. Okay, so it's going to be volume, not the volume in this particular case is not going to be equal to pi r squared h. It's going to be volume is equal to 1,000 pi r squared h, because we have to specifically account for this being in liters and our measurements, our radius and height measurements being in meters. So we have to multiply by that 1,000, that conversion factor, so everything kind of like corresponds. Okay, so where a lot of students want to make a mistake in calculus, that they would just go ahead and just use this, okay, and just keep plowing away and plug in their liters and whatnot, but without doing that conversion factor. So this is not a small point. That's why I spend some time on it. So really, hopefully let this sink in, because this problem that we're covering here, that I'm covering, is a super classic type of calculus problem. So you'll see it again for sure, and you want to practice it a lot in all kinds of different variations. That's why that particular book is really good, because it's a lot of problems, and that there's a lot of solutions to a lot of different problems, okay, of all types. So anyways, let's move forward. Okay, so hopefully now you're like, okay, I totally understand, okay, what he's talking about. And now let's move on here. Okay, so our formula that relates both the V and the H is the following. Okay, all right, so now we're kind of getting to the fun part. So the fun part is we're going to be thinking in terms of calculus, right? We can differentiate both sides with respect to t. So we have an equation, and in calculus we can think of certain type of equations where we want to differentiate with respect to another variable. This is a whole nother side topic, like what type of functions can be you can differentiate. Again, I'm just going to kind of talk about this in general terms, but just know this: you can differentiate a function if the derivative exists. And so here the derivative exists with respect to time. So in other words, hey, with respect to time there's going to be some volume, and with respect to time there's going to be some height. Okay, so basically that means that we can differentiate both sides of this equation with respect to t. So that means that we have this v here, okay, we have this v, so we're just going to write dv dt, right? This is differentiating volume with respect to time. And now we're going to do the same thing with this h up here. So here, well, let's just go back with the v. All right, I'm going to differentiate that volume with respect to time, and then I'm going to differentiate this height with respect to time, so I'm going to get dh dt. Now you might be saying, well, there's another variable here, r. Well, the radius in this particular problem is constant, right? Let's kind of scroll back up here. So the radius is not changing, okay? Like if I got whatever cylinder I'm having, the radius is staying the same. The only thing that's moving or changing is the height and the volume. That's why the radius remains constant, and we're not going to mess with it, okay? So hopefully you can see now. You say, okay, we differentiated both sides of this equation with respect to t, or time, so this is what we're left with. Okay, so let's get to the part where we can find the solution here. So here we had dv dt. Okay, so we have this. Remember, we know that dv dt is negative 3,000. So this is something we can plug in, and we need to solve for the dh dt. All right, so let's just go ahead and plug in what we have. Remember, dv dt is negative 3,000, so I could just substitute dv dt with negative 3,000, and I'm looking to solve for dh dt. So you can kind of think of that as just a big variable, like a big x or whatnot. So we're just doing basic algebra at this point. And then r is constant, so that's just a number. So this whole part right here is just some big constant number. So all I need to do is divide both sides of the equation by the 1,000 pi r squared, and I end up with this. Negative 3,000 divided by 1,000 pi r squared gives me my dh dt, and that is what I'm looking for, right? So when I simplify this down, I'm left with this. Okay, so dh dt, or the change of height of this particular cylinder with respect to time, is negative 3 over pi r squared. So that is the solution. You're like, okay, that's great, but like, what does this mean? Like, what's the meaning to it, right? So let's talk about the meaning. All right, so let's go down here, and this is the essence of calculus, okay? In terms of the related rates of change, like we use this equation, all right? We have a specific kind of equation to help us determine how fast the fluid level is going to drop with respect to time. Okay, we can just use this particular formula, Okay, when we have cylinders that are being pumped out at pumping their fluid out, or their fluids being removed at negative 3,000 liters per minute. So if we're pumping out at negative 3,000 liters per minute in a particular cylinder. Here I have two different cylinders. If I want to know how fast the fluid level is dropping, I can just use this. Okay, so let's take a look at two examples. Here I have one cylinder, and let's call this particular cylinder, it has a radius of 1 meter. And then let's say this cylinder over here has a radius of 10 meters. Now, we already talked about in the beginning of this problem that the skinnier the cylinders, we would expect to see the fluid level drop faster, right? Here, in a real wide, kind of tank cylinder type of scenario, we would expect that with the same removal rate, that this is going to be like slower, right? We would see this fluid level drop slower than this fluid level. So let's see how this pans out. So let's take a look at what the rate of change is. Okay, dt is going to be when it's 1 meter. So here is our solution. And you can see here, all I need to do is just plug in the radius here, and that is 1 meter. So here's just the math, or I'll spare you all the details. But we end up getting negative 0.95 meters per minute. But as most of you are probably very familiar with the metric system, negative 0.95 meters is the same thing as 95 centimeters. So let's just use this number, and I'll tell you here in a second why. So I'm just converting 0.95 meters to 95 centimeters. So in this scenario, okay, when we have a tank that has a radius of 1 meter, okay, and the fluid's being removed at 3,000 liters per minute, we would see that the height, the fluid level, drop 95 centimeters per minute. Okay, so keep that in mind. Now let's go back over here to our other tank where we had a real wide radius, say 10 meters, and let's do the same calculation. Okay, so again, we're using the same solution. Okay, dHdt, same answer, but obviously the radius is different. It's 10, so that's going to be 10 squared. So here is the math. And when we do all the math here, we end up getting negative 0.0095 meters per minute. And when we do the conversion from meters to centimeters, this is equivalent to not even 1 centimeter per minute. It's negative 0.95, not 95, negative 0.95, not even one complete close to 1 centimeter per minute. Okay, so this tank is dropping, here let's just use the real round numbers. This tank is dropping 95 centimeters, okay, centimeters per minute. So this is much quicker than something that's almost, let's just call it approximately 1 centimeter per minute. Okay, much slower, much quicker. Okay, and of course, when you have a solution like this, all we need to know that, hey, we're dealing with a particular tank or cylinder of whatever level, okay, at this fixed rate of change, okay, and in terms of this removal rate, as long as it stays constant, we can look at any kind of tank and use this formula here, this for dHdt, to give us the how fast the fluid level would drop. So this is what we're talking about, related rates of change and application of the first derivative. Super classic problem. Guarantee you'll see it in many forms. But let's go ahead and wrap up this video. Hopefully this makes sense to you. I'm pretty sure it does for a lot of folks. So again, I can't recommend that particular book enough. It's a great book. There's other books out there, but I believe there are still some, the book still exists. So I'm going to leave a link to it in the description of this video. So check that out. It's called The Humongous Book of Calculus Problems, and it's just a bunch of solved problems. Really, really good. Because when you look at a calculus text, there's a lot of good calculus text books out there. They may only have like 1 or 2 or maybe 2 or 3 different type of solved example problems. This particular book has many more, so that's why I really recommend it. Anyways, I hope you consider subscribing to my channel. Again, my focus is mainly middle and high school mathematics, but I do also calculus videos. So if you enjoy my videos, hopefully you consider subscribing. Hey, if you like this video, definitely appreciate a thumbs up and leave me some feedback. Um, you know, are you in Calc 1? Are you in Calc 2? Are you in pre-calculus? Are you just curious about calculus? Any kind of feedback would be good. But again, calculus is one of those subjects that really it's an amazing mathematics. Okay, I mean, and it's solved so many problems for us. It's unbelievable. So I mean, of course, as a math person myself, I might have more appreciation than a lot of people for it. But it's funny, and that's about just the word calculus. People know that word, that don't even have a clue about calculus. Oh yeah, calculus, it's this crazy math you do in college, but they don't really have any idea what it's about. And I think that's what motivated me to do that particular video a couple years ago, the time of this video on Understand Calculus in 10 minutes. It's funny, that video actually went much longer than 10 minutes, but for whatever reason, people didn't seem to mind because I kind of explained the real basics of that, of what calculus, at least in my ideas, try to express in real basic terms the essence of calculus and why it's so powerful. But with that being said, I definitely appreciate your time. I wish you all the best in your study of mathematics and calculus. Okay, whatever. And there's just one last comment. If you are in fact a calculus student in college or whatnot, it's going to get challenging. It's going to get difficult. My best advice to you is don't give up. Don't give up. Just keep working hard. Eventually, light bulbs will start clicking, and then you'll get through. But real typical experience for calculus students, especially Calc 1, Calc 2, it's like a tsunami coming at you. It's a lot of information. It's new. It's abstract. So you got to stick with it. But if you do stick with it, you will understand it. Okay. All right. So with that being said, thank you for your time and have a great day.